So here is kind of the very quick recap version of yesterday. We're talking about quadratic functions. They come in two varieties of forms. One, the standard y equals x squared plus bx plus c, just descending order of terms. Again, the square term is the thing that makes it quadratic, right? So that's the leading or the highest order term is the square. For those, A tells me about which way the thing opens and something about the shape. So if A is positive, it's opening upward. If it's negative, it's opening down. If A is, I don't know, 2, that means it's going to be sort of a taller, like tighter, skinnier parabola. We can also just read off the y-intercept as C, because if I plug 0 in, these terms drop off, and we just get C, so that's kind of nice. We do have a quick, little shortcut formula kind of thing to get the vertex. Vertex is at negative b over 2a for the x value, and then plug that back in to get the y. Again, vertex is important in a lot of applications and for a lot of reasons, so we want a kind of quick way to get that. The other is the vertex form, or kind of the transformation form, like the one that we're used to seeing, really, where I can just read off, shift it to the left and off or whatever. That looks like this. The vertex is just HK because again, we can read off the transformations. The A here is the same A as this if I multiply everything out, right? So it does the same thing. Positive would be opening up, negative would be opening down. 2 would be a stretching thing, half would be a shrinking thing, that that whole thing still. Again, nice because I can read the vertex off, and then today we'll get into solving equations and see some more about kind of where these two different things show up and how they work. I think yesterday we pretty much left off here. I don't remember if we worked through all or any of these to actually get answers, but we talked about where we would find these things on number 5 on the back, the projectile motion thing. But there are the actual answer values that you should have gotten. We'll talk about the barn thing and maximizing area in a second, but the other big thing we did yesterday was look at completing the square. Is there anything that we need to talk about more or take another look at from yesterday? Or we feel okay about things so far? Anyway, okay, so we can revisit stuff as needed. Just let me know. The barn thing here, this maximizing area thing, I definitely want to talk about because this is a little bit different. There's a little bit of setup stuff required that's not totally obvious where it comes from. So this farmer has a barn that's too big a barn. So there's a barn here. There's a garden next to the barn. That's the garden. He wants to fence it in. I noticed that I didn't actually say in the problem, but we're going to build a rectangular thing. Like all we're really equipped to handle right now is dealing with rectangles, but we're going to build a rectangular fence around the garden. The garden sits next to the barn, so he doesn't need to fence in the barn wall, right? Like he's going to leave that open and just put the fence sort of coming off of it. So the part that's actually fenced is going to look like this then, basically, right? A rectangle, but he only needs to build 3 sides of it because the barn wall is there. He has 180 feet of fence to use, doesn't need to fence in the side next to the barn. What is the maximum area that can be enclosed? Okay. So apart from the geometry, right, like getting the diagram from the description of what's going on, there are 2 things here that are relevant in terms of the math, in terms of what we need. One is that there's 180 feet of fence to work with, right? That puts a constraint or a restriction on what he can do. If the question was just what is the maximum area and he had unlimited fence, well, figure out how to build it so that you have half the world split up and there you go. Like that's the maximum area, right? But it's not. There's a restriction. He's got 180 feet of fence to use. And then there's the objective, the thing that we're trying to do, which is to optimize or maximize the area. So there's a condition or a constraint, and that's on the perimeter of the fence. And then there's the objective, which is to find the maximum area. Okay. There's not a whole lot of stuff that just at face value in this paragraph looks like, a math problem, though, which means we have to, find it. We have to set it up. We've got a diagram, right? Here we put it together. If you might be given the diagram, you might have to assemble it, but a rectangle, we need to build three sides of it. What do you know about rectangles that's going to be useful here or helpful? The sides that go the same way are the same length, right? So this side and this side are the same length. Let's label them. What do you want to call it? A. Okay. A? Can I use something other than A because I'm going to talk about area? I don't want to save A for that. So what else you got? X? Okay. L, W, whatever. I just don't want to use A because I'm going to use it for area. If this side is X, then so is this one, because they're the same, because it's a rectangle, and that's how rectangles work. What about this side? It's the same as the top one, but I don't need to build the top one because it's already there, right? We're using the barn wall. So what I need to build are two of those, but just one of whatever this is. Okay, well, I want to label this also. Since we used X, I'm going to use Y to label that one. The one thing I don't want to use to label that side is X, because I've already used X. And if I call that X, then I'm saying that all three of them are the same and all three of them aren't the same, right? Or they might not be. I don't know if they are yet or not. Turns out they won't be. But I don't want to assume that they are, so I need to label it something different. Is that okay? Okay, so length and width, right? They need to be different things. If they turn out to be the same in the end, then like great, that happens. But I don't want to go into it assuming. Then what does our constraint about the amount of fence he has to work with tell us? We need to build X and Y and then another X, right? If he wants to build this thing as big as possible, how much of that 180 feet of fence should he use? All of it, right? It doesn't make sense to leave leftover because then you could have built it bigger. So this constraint, this perimeter thing, well, I need to build two X's and a Y, and I need to use 180 feet of fence. So that would look like that, right? X plus Y plus another X, or 2X and Y would be 180. Just to, sort of label things. That's again, that's an equation version of our constraint, our restriction, right? Okay. The thing that we're trying to do is find the maximum area. What's the area of this rectangle? What's the area of any rectangle? Length times width. The length and width here we've called X and Y. So I need to find the maximum possible value of this subject to this, right? With this restriction and how X and Y are related. Any ideas how we can do that? This thing that we're trying to maximize, it's got three things that I don't know what they are yet, right? I don't know what the area is, because if I did, I wouldn't have to do anything. We'd be done, right? I don't know what X is. I don't know what Y is. Okay, well, I don't know anything at all here. That's probably not the first thing I want to look at then. Here, I don't know X and Y, but at least I know something about how they relate to each other, right? 2X and a Y add to 180. what can I do with this to help me figure out more about what's going on there? What if I figure out how to write one of these in terms of the other one? Right, this tells me about how X and Y are related to each other. If I figure out how X and Y are related to each other in such a way that I can reduce this to fewer variables, that would be good, right? That feels like it's moving in the right direction. So solve for either X or Y here. Which one do you want to solve for? Okay. So if we solve for X, subtract Y. And then divide by 2. So 90 minus Y over 2. Or 2x plus y equals 180. So y is 180 minus 2x. Either of those works, right? Solve for one or the other. This is x in terms of y. This is y in terms of x. What I want to do with that then is use it to substitute into the area equation, right? The objective, the thing that I'm trying to actually do. If x is the same thing as 90 minus y over 2, then where there's an x here, I can replace with that. Okay? So area, in place of, well, which way do you want to go? You want to replace x with this or replace y with that? This feels like a little bit simpler, right? Either way is fine. It's going to work out the same either way. I agree that this feels a little bit easier to deal with. So in place of y, I'm going to put 180 minus 2x. Again, either way is fine. It doesn't make a difference, except for how you feel about it, maybe. Just write that here. Okay, so what we did is take this and replace that. Okay, and now there's some algebra that, looks like it ought to be done over here, right? Distribute that x. Just for emphasis, I'm going to rearrange. Get out of here. Now what does our area equation say? Before it was just the abstract, like here's a rectangle, its area is length times width, right? Now it's still area, but it's in a single variable, right? We've written it just in terms of x. And what kind of equation is it, or function is it? It's quadratic, opening down in standard form, right? The c term's 0, but who cares? It's a quadratic that opens down. What are we trying to find again? We have area as a quadratic that's opening down, and we want to find the maximum area. What do we need to look for? The vertex. So this thing, area as a function of x, it's quadratic and opening down. Find the vertex. And as you go through homework and stuff, especially like the 3.2 stuff, the answer to basically every question is going to be find the vertex, right? Like that's what we're looking for. Anytime you see maximum show up or minimum, at this point, that's probably going to mean finding the vertex. So we need to find the vertex. Again, this thing is, standard form. I've got a is -2 and b is 180. So x equals -b over 2a, negative b over 2a, and that's 45. And does that answer the question? No. Grady's very hesitantly shaking his head. No, it does not. What was the question? Find the maximum area. What did we just find? I don't know what I'm counting. We just found one of the sides, right? We just found X because we wrote the thing in terms of X. We called the side X in the, oh shoot. We called the side X in the first place. This side is 45 feet. And this side then is also 45 feet. And if those two sides are 45 feet, what's the area? Or how do I find the area? Length times width. Okay. If those are both 45, then what's the other side? 90. How do you know?
Because you have to use a maximum of 180.
There was 180 to begin with. You took out 45 and then 45 again. That's 90 left over, right? You can take 45 and plug it in here if you want. That gives you 90. You can take 45 and, just think through what's left over. That also gives you 90. Whatever version of that makes sense for you is fine. The dimensions then that give the maximum area are 45 by 90. And the maximum area itself would be 45 times 90. Shoot, I just did this an hour ago. 4,050. Right? Oh, yeah. Yeah, 4,050. I can multiply. 4,050 square feet. That would be the maximum area. If you want, you can also you can take 45 and plug it back into this area function, right? That would give you the same thing because we found area as a function of x. If we give it an x value and plug in, that would give you the same thing. The maximum area though is that 4,050 square feet. Okay. Questions about any of that? Kind of two pieces, like what are we trying to do and what do we know? And then use what we know to figure out more about the thing we're trying to do, right? So the thing that we know is, again, this constraint, this restriction, the perimeter thing here, right? Use that to figure out how to write one in terms of the other and substitute into the area the thing that we're trying to actually learn about and do. So that I end up with a quadratic, so that I can find a maximum. The thing that changes in these, once you have kind of the general idea, the flow of how this goes, the thing that changes is the geometry. So take a look at number 7 on the notes, which I assume you have in front of you. An elementary school wants to fence off a rectangular There's a rectangle playground. Here are some children and a slide and a swing set so that you know it's a playground. One more child. Okay. Elementary school wants to fence off a rectangular playground, then divide the playground in half by another fence that is parallel to one side of the playground. Divide the playground in half by another fence that is parallel to one side of the playground. What does that mean? You're cutting it in half. What about the parallel to one side thing? Okay. Doesn't necessarily have to be the short side. We're cutting it in half, but we're not cutting it in half in a weird way, like diagonally or something, right? That's all it means. So we're cutting it in half this way or this way. It doesn't matter which way we draw it because I don't know yet enough to draw it to scale anyway, right? So the picture may end up looking, wrong when we get to an answer, but I don't care about that. I'm just using the picture to help me set up that, really set up the constraint thing and what the area is. So I just need to divide this in half somehow. That will work. And again, really, I'm using this to help me figure out, how to write down the constraint and write that as an equation. So the school has 450 feet of fence to use. What dimensions will maximize the enclosed area? What is the maximum area? Okay, so the question, the thing we're trying to do is basically the same. What do we need to build with that 450 feet of fence? How should I label this diagram to help me get there? Okay, let's call this something. Maybe that's L. What else is L then? The one that splits it in half, and then that side. Those are all the same. Oh, shoot. Those are all the same. Okay, what do you want to call this? I used L, so I'm going to use W, but again, the labels don't really matter, right? Then that means that this one is also W. What does our constraint, our restriction, our perimeter, if you want, equation look like then? We got 3 L's and 2 W's, and they should add up to 450. What's the area? Is that splitting it in half down the middle? Does that have anything to do with the area? No, it doesn't matter, right? It's still length times width. Okay. After that, you're just going to do the same stuff, right? Solve this for either L or W, substitute that in here. You get a quadratic that opens down, you need the maximum, you find the vertex, you follow the bouncing ball. So the difficult part again, I mean, I know it's, you know, the first time you're trying one of these on your own or whatever. So like that's got some stuff to it. But once you get the hang of that, like what to do, and the difficult part is making sure that you've got the thing set up and labeled correctly, and then interpreting that to get this constraint equation. Okay. So I'm going to leave this one off here and let you finish it. If we need to, you know, come back to revisit it on Thursday and talk about it, that's fine. But you go try this one on your own, do some of the ones in the homework, and make sure you kind of have the feel for that. If we need to come back to it on Thursday, we will. Okay? Okay. All right. Today, then, we're going to talk about solving quadratic equations. Okay, solving quadratic equations. So, you know, we know how to deal with the functions now. Basically, we're asking, okay, if I take some quadratic function and I want to know where it's equal to 0 or 2 or 7 or whatever, how do we find those intersections, right? How do we find those specific points where that happens? Now, before we jump into how to actually do it, if we're solving an equation where I take a quadratic whose graph is a parabola, which is definitely not 1-to-1, right? It's, you know, 1-to-2 or 2-to-1 or whichever one means which thing, I don't know. But probably what we should expect going in is that often there are going to be 2 solutions, right? Don't have to be. Sometimes there's one, sometimes there's none, but often there are going to be 2 because of the way the graph works, and, you know, it's just how it is. Because of that, because it's not 1-to-1, that means it's not invertible, right? That's what 1-to-1 was. Anytime you have a function that's not 1-to-1 and you want to solve an equation, well, the way that we would like to do equations is by doing the opposite thing to sort of get rid of stuff, right? Because it's not 1-to-1, what the opposite thing is not as well defined, right? Which means there's kind of more to the equation solving thing, right? So there's going to be more to it often than just, you know, moving things from one side to the other. Like solving a linear equation, all you have to do is push stuff around. The reason that all you have to do is push stuff around is that's one-to-one. So I know exactly what the opposite things are. I just do the opposite things until I don't have any more things to get rid of, right? That's not true here, which means that the solving is kind of a little more involved. So we're going to look at a couple of different methods and tools to do this. Let's start with the zero product property. Zero product property says if I have two numbers and I multiply them and get zero, multiply two things and get zero, or three things, or a million things, or whatever, multiply stuff together and get zero, take a product that's equal to zero, then what do you know? One of them had to be zero. If I multiply stuff together and get zero, well, they can't both be positive. They can't both be negative. They can't be mixed positive and negative. One of them has to be zero in order for the product to be zero. So either A is zero or B is zero. Or both, right? If we don't know that they're different. If we know they're different, then one of them has to be zero. If they can be the same, they can both be zero, whatever. But like that has to happen. Zero has to be in there somewhere. Okay. So to solve an equation, then this is quadratic, right? The thing on the left, it's factored. But if I multiply it out, it'd be an x squared. So it's a quadratic. It's factored though and equal to zero. Well, forget about what these things are for a second. What we're doing is multiplying two things and getting zero. You multiply two things and get zero, what do you know? One of them is zero. Okay, well, one of these things is zero. Either this is zero or this is zero. Well, okay. So either x plus 1 is 0 or x minus 5 is 0. That lets us break it up into a smaller, simpler, linear equation to solve using, again, this zero product property idea. If x plus 1 is 0, then x is -1. And if x minus 5 is 0, then x had to be 5. There you go. Those are your solutions. -1 and 5, those are the two solutions to that equation. Those are the only two solutions to that equation. Anything else that I plug in there, I'm not going to get 0 when I multiply. Okay, great, cool, awesome. So if we have a product of things, it doesn't have to just be two things. We'll do this again in a week with, 4 terms, and you multiply, excuse me, 4 terms, and you multiply and get 0. That means one of them had to be 0. How is this useful if I'm trying to solve something like this, though? If I can factor it, then we're good to go. Okay. Well, again, I've got equal to 0. So what I'm going to try to do is factor. And factor. Okay, so take the 2 out of everybody first. Okay, I like it. Okay, how? Why? Yes, but
when you add 2x and 3x, you get 5x, and then 2 times 3, you FOIL it.
Okay. So we're trying to, again, like undo a foiling thing, right? Undo an expansion. The way that works, if I'm trying to guess at what the factors are, I'm looking for things that multiply to 6 and add to 5. So factors of 6, or nice factors of 6, are 1 and 6, or 2 and 3. This last term being positive means they have the same sign, right? They're either both positive or both negative. Okay, so my choices then, my options are +1 and +6, or +2, and +3. Those would add to 7. I want them to add to 5. So it's gotta be +2 and +3. In some sense, we're doing a thing kind of like the completing the square stuff we did yesterday. I'm trying to break this up. I'm not trying to force it to be a perfect square anymore, but using the sort of, educated guessing thing that we just did, I figure out that if I break this middle term into 2x and 3x, then I'm going to get factors that work out to give me what we have. So that's how that would factor. Easy enough to check, right? Just multiply this back out. X times x is x squared plus 3x plus 2x. That would add to 5. And then 2 times 3 plus 6. If you have some other way for factoring, like some people draw like a little like box thing or like a, I don't know, like an X. I don't know how those things work, but like whatever you do for factoring is fine with me. You are, in theory, meant to know how to factor before you come into this class. But if we need to talk about it in office hours or something, then please come by. There's nowhere that we're going to like strictly have to be able to factor. So if you don't feel super confident about that, practice a little bit, try to get better, but don't worry about it too much.
So what would you do with the 2 that's outside of the parentheses?
So that was kind of a sidebar, right? What we just figured out is that this thing I can write like that. Now, again, we've got a product equal to 0, right? 2 times x plus 2 times x plus 3 equals 0. So let's go one at a time. Can 2 equal 0? No, because 2 is 2, right? 2 is a number. 2 is not 0. So forget about it. If you want, you could just divide both sides by 2 and the 2 goes away. 0 divided by 2 is still 0. Can x plus 2 be 0? Yeah, x can change. So x plus 2 can be 0. So again, we're using this 0 product idea. X plus 2 equals 0. That's one possibility. And that happens when x is -2. Can x plus 3 be 0? Sure. That happens when x is -3. So there you go. There's your 2 solutions, -2 and -3. So that 2 outside turned out didn't really have anything to do with anything at all in terms of solving the equation. Okay, so factoring this 0 product idea, and again, I'm going to keep making a big deal about the 0 thing. Multiply 2 things and get 6, or anything but 0. Do you know anything at all? Could be 1 and 6, could be 2 and 3, could be 12 and a half, could be infinitely many things. I don't even know if they're both positive, right? They can both be positive, they can both be negative. I don't have any idea. I know nothing about this, so I cannot do the same thing and split it up and solve them individually, right? That's why the name of the thing is the 0 product property. 0 is important, 0 is special, 0 works differently. I'm going to keep writing this. I think it would be a good idea if you do it too, so that you really, burn in your brain that like this only applies to 0. But anyway, there we go. If we can factor, then we're good to go. The problem is that factoring is difficult in general and not always something we can do, right? When it's, little toy examples like this where I can just sort of guess the factors pretty quickly and easily, like, great, that's awesome. But doesn't always work. Factors aren't always pretty. So other stuff. Okay, well, what if we know about the square of a number, right? Quadratics, the whole quad part is talking about a square. The defining thing is that square term. If we know that the square of a number is 4, then what could that number be? No, the square is 4. You take a number and square it and you get 4. 2 or -2, right? Okay, so if we know that the square of a number is 4, in other words, x squared equals 4. And we're trying to figure out what x is. Well, how would I solve
that? What's the, you know, sort of most direct way to go at this? You have a square, you want to get rid of the square, do the opposite. The opposite's the square root, right? Okay, well, the square root of 4 is 2, so cool. There's a little bit of a technicality thing here that we may not always think about. X squared looks like this, right? It's a parabola. What does the square root function look like? Just like that. It's a sideways parabola, but it's only the top half of it. Because this isn't one-to-one, when we do the opposite or undo it, we get a kind of weird thing happen, right? What that means is when you take the square root of x squared, and I don't know what x is yet, I don't just get x, I get the absolute value of x. If the absolute value of x is 2, what could x be? 2 or negative 2. Now, most of the time, we don't, and I won't, moving forward, write out that absolute value thing, because like that feels weird, right? It is what's happening, but it feels weird. Most of the time, what most people would do is say, well, the square root of x squared is 4. Okay, then x is either plus or minus 2. And basically think of it as if I do a square root somewhere, if I choose to use a square root to do something, then what comes along with that is a plus or minus, right? The square root symbol always means the principal or the positive one. That's why your calculator gives you back just the positive root when you push the button. But because we're using it to do something, there's like an implied plus or minus that comes with that, okay? And that's a, weird, I got to remember it thing, but that's what it is. Okay. Can I erase that part? Okay, that you would rather not think about anymore anyway. How does that help for solving something like this? This is still quadratic, right? There's an x squared in there. It's, hidden a little bit, but we've got x plus 1 all squared on the left equal to 9.
So what you do is you break it up in factors, so you get x plus 1 in the parentheses on both sides equals 9, and then you left with x plus 1 equals 9, and then it can be either positive or negative.
Right track, but be a little bit careful. We can't split it up like that. Like, even if you think of it as x plus 1 times x plus 1, you can't split it up because this isn't 0, right? So it works a different way, right? So we can't split it up quite like that. But the thing on the left, forget about this. The thing on the left is a perfect square, right? What's the biggest or like outermost layer to the stuff that's happening on the left-hand side? The square, right? The square is the like outside. That's the last thing that's happening there. Well, how do you undo a square? A square root. Okay. So if I take a square root of the thing on the left-hand side, what's going to happen? The root and the square are going to cancel. I'm just going to have x plus 1 left. That's great. That's what I would love to have happen, right? I would love that square to not be there anymore. And that's great. That's what happens. But if I do a square root on the left, I have to also do a square root on the right. And because I'm choosing to take the square root, right? All this absolute value stuff applies, and we get plus or minus the square root of 9, right? Not just 3, but also negative 3. Again, this is all going back to quadratics not being one-to-one, so weird stuff happens, right? That's why we get two things here. That says that x plus 1 is equal to either positive 3 or negative 3. And I kind of showed you that like there's a hidden, sort of absolute value layer in here. Well, this takes on an absolute value kind of feel then when you solve it, right? It's one of those two things happening. So I split them up and I solve them separately. If x plus 1 is 3, then x is 2. If x plus 1 is negative 3, then x is negative 4, right? This is not the only way we could have done this. I could have taken the x plus 1 squared and expanded the whole thing and then collected everything to one side and then try to factor. The fact that the solutions came out to be, pretty nice means I probably could have factored it. So like that would work. You can do some algebra on the front end and then collect things up and factor. We're going to talk more as we go about like when to do what and how to decide and whatever. But ultimately, all I really care about when we get to, testing or whatever is, hey, here's an equation, solve it, right? Like, I don't care how you do it. So, there are times when one way might be a little quicker or easier than another, but ultimately they all go to the same place. Okay, so if there happens to be a perfect square in there, then this is really convenient, right? Like, this is a nice way to get rid of that at the cost of, again, sort of remembering that plus or minus thing. But apart from that, it's pretty clean, pretty straightforward. For something like number 4 then, which I'm going to leave for you to do, same idea, but first I need to solve for that. Move stuff around, so add 1 to both sides, divide both sides by 2, get the square term by itself. Because when you take the square root of a square term, things cancel and you just get the stuff inside, right? 16, so, you work out the details, but should end up there, and then you can do a square root, and then you can go on and, finish the thing. You do this. Okay. So we've got factoring, right? Factoring is cool. Factoring, once we get the thing factored, the actual solving, like finishing part is pretty straightforward. We just split them up. We solve, much smaller, simpler equations and we're good to go. Problem is we can't always factor, right? And sometimes even when we can, it's a pain, right? So can't always factor, or, it's difficult sometimes even if we can. Square root property. Again, like fairly straightforward and painless. Once we get to the point that we can use it, the square root gets rid of the square, which was the kind of, messiest part of it anyway. We get this plus or minus term. You can use this kind of anytime you want because you know how to complete the square now. So you can take a thing that's not a perfect square, you can force it to factor like 1 by completing the square. You can move stuff around, you can, solve using this idea. That's probably the long way to go in a lot of cases, but it's an option. You can do that. Neither of those things are really good, like just, do this every time kind of things. Like neither of them really works all that well all the time. The quadratic formula, that's like the nuclear option. So the quadratic formula, this is the, great hammer of justice that like I can use every single time. And every single time it's pretty much the same. It's always kind of a medium amount of hassle, but it's like the same medium amount of hassle every time, right? Like it's my medium amount of hassle. I own it. I know how to do it. Basically, if you take a thing in standard form, like ax squared plus bx plus c equals 0, and the equal 0 part is important, right? Got to have everything on one side. If I take that and complete the square and move stuff around and use the square root property and go through, big old 12-step calculation stuff, I get that x equals, do y'all know it? Does anybody want to sing it? No? Okay. I always put it to the tune of Pop Goes the Weasel. You decide for yourself how you want to, keep it in mind. But negative b plus or minus the square root of b squared minus 4ac all over 2a. Okay. I'm still not a big like memorized formulas guy, but this one's, there's just kind of not a lot of way to get around it. Like you kind of need this one. The good news is by the time the test rolls around in a couple of weeks, it's just going to be etched into your memory anyway, like whether you want it to be or not. So like, it's not going to be a big deal, but there it is. In the meantime, look it up when you need it, but, try to come up with it on your own first. But we take A, B, and C, the coefficients, we peel the coefficients off, we mush them into this formula in the right way. Notice it's got a plus or minus in it. So really there's 2 things there, right? And we do some arithmetic and ta-da, the solutions, fall out. So x squared minus 2x minus 4 equals 0. I don't see a perfect square thing in there. right? A like factored perfect square in there. I could complete the square, but I don't want to. This doesn't factor because if you think about factors of 4, 1 and 4, or 2 and 2, right? There's no way to get this middle term to come out right. So, you check if you want, convince yourself. When it comes to, doing something with a time limit, like on a test, think about factoring for a minute. If you don't see it, then move on, right? Because even stuff that looks like it should doesn't always, right? I'm gonna go to the quadratic formula then. Again, if you want to just do this every time, you do this every time. It's fine. I don't care. What are A, B, and C? A is 1, B is -2, and C is -4, right? So quadratic formula, X is the opposite of B, negative B, right? What's the opposite of B? 2. Plus or minus? Big square root, B squared. B is negative. When you square it, that's going to be positive then. Minus 4 times A times C. All over 2A. And now it's an arithmetic problem. -2 squared is 4. Minus 4 times 1 times -4 becomes plus 16 all over 2. Square root of 20. Is 20 a perfect square? No, shoot. If we're looking for exact values then, which we often will be, I need to break 20 down. It's 4 and 5. 5's prime, but 4 is 2 and 2. So the square root of 20 is 2 square roots of 5. This is my point about the quadratic formula always kind of being the same, like medium amount of hassle, right? It just always kind of feels like this, right? If that's a perfect square, then like cool, it feels a little bit more straightforward, but it just kind of always goes about like this. Now, 2 plus or minus 2 root 5 all over 2. There's a lot of 2's there, right? How does that simplify? I don't really want to get into multiplying, like changing things, because I'm just trying to simplify what's already there, right? So if I do something to that, like multiply, then I got to do it on the other side, then I got to worry about taking it out later, right? So I just want to try to simplify what's already there. Now the plus or minus, it's in the numerator, right? The way fractions work, addition or subtraction in the top, you can split up. So I can break this up or think of this as 2 separate fractions. 2 over 2 plus or minus, it really is plus and minus, right? It's 2 separate things. 2 square root of 5 over 2. What's 2 divided by 2? 1. What's 2 square roots of 5 divided by 2? Square root of 5. That's your 2 solutions. 1 plus root 5 and 1 minus root 5. For stuff you're going to hand me, I'm fine with you leaving it as plus or minus like that. For stuff that, in my math, I want you to list them out separately. 1 plus root 5, comma, 1 minus root 5. But that's the way that you simplify something like this. If you're going to reduce, you have to be able to reduce kind of in both places, right? So you want to think about it as 2 separate fractions. All right, there's another one there, 6, that you can try. I also want you to give this stuff on the back a shot. The inequality problems in 7 and 8, do those the same way you would do an absolute value. Solve the equation first, then think about testing and stuff. Number 9 is similar to the football thing from yesterday. Just make sure to think about, what it's actually asking. So between now and Thursday, attempt at least. There's no reason you shouldn't be able to just do all of them, but the stuff in the notes. 3.2 homework you should be able to knock out if you haven't already. 3.3 you can get a good start on at least. Thursday, we'll talk about imaginary numbers. That's the other section there. All right. Y'all have a good day. I'll see you then.